In this video, we're going to talk a little bit more about confidence intervals. So, a bottling machine is operating with a standard deviation of 12 hundredths ounces. Suppose that in a simple random sample of 36 bottles, the machine inserted an average of 16.1 ounces into each bottle. Find a 95% confidence interval for the mean. Alright, so we have a point estimate here at 16.1. So we're going to build our confidence interval around that. It's going to be 16.1 plus or minus, and of course 95% confidence means we're talking about 2 standard deviations away. Okay. Now I'm just going to put a blank there for a second. And I just want to make sure you remember that if we were talking about where are 95% of all bottles, what's an interval that covers all bottles? We would just put 0.12 inside those black brackets. But that's not what a confidence interval does. A confidence interval gives us an estimate of the mean. And sample means have less variability. So instead of using just standard deviation, we use the standard error. So we do standard deviation over the square root of sample size. So what this comes out to be, if you calculate it, is 16.06 to 16.14. So there's our confidence interval. Now, to interpret the confidence level, the confidence interval, you've got to remember that kind of fill in the blank thing that we used the other day. Okay, so we are 95% confident that the interval from 16.06 to 16.14 captures the, and now this is where you have to fill in the actual parameter in context. So the actual parameter in context is the mean for the bottling machine. Now, for a confidence level, again, we've got to remember our kind of fill in the blank sentence that we use. So for confidence level, our interpretation is this. If we take many samples of the same size from this population, about 95% of them will result in an interval that captures the actual parameter value. Okay? So pay very close attention to those two, because you'll notice the interval almost is a more applicable thing. We actually have numbers. We say, hey, we're pretty confident that the actual mean is somewhere in there. Where the level is more kind of overall, what did this process say? It says that if we did the same thing over and over and over again, about 95% of our intervals would capture the actual parameter value. Okay? So make sure you pay attention to the difference. Now, it's just kind of a quick follow-up question. What would happen to the width of an interval if the sample size increased? Well, the width would decrease. And this is just simple algebra. If you've got a deviation and you're dividing by the square root of n, as n gets larger, then the standard error gets smaller, and therefore the interval gets smaller as well. Now, what would happen to the width of the interval if the confidence level increased? Well, for this, you really have to think about what's going on. We're setting this up to say, well, we want to capture 95%. So if I change my confidence level to be, say, 99, what happened to my interval? Okay, well, it got wider. A lot of people, that throws them off. They say, well, how can confidence go up with a wider interval? It really just gives you more room for error. It's, it's no different than a weather report that says, well, it's going to be anywhere from 10 degrees to 90 degrees. Well, with a wide interval like that, chances are pretty good you're going to be correct. So our confidence in our prediction can increase if we make a really wide interval. So then the follow-up to that is, if large sample sizes are better, why don't we just make larger sample sizes? You'll always read things that say like, well, there was a margin of error of 3%. Well, if you could ask more people, why not do that? Usually, a larger sample size, it takes a huge increase in sample size to get a modest decrease in margin of error. And that really has to do with the fact that we're dividing by the square root of n, not just n. So if you think about, increasing from, 400 to 900, think about that really isn't changing your denominator by all that much. So it's usually simple time and money is why we don't take the time to actually ask more people or take more samples. Usually we just say, you know what, plus or minus 3 is more than good enough. And just remember, we have our conditions here. So our condition 0 is always that it came from a simple random sample. And from there, our condition 1 is that our sample size is less than or equal to 1/10 the population size. And then, depending on if it's a proportion or a sample mean problem, of course, we can have a different sample or a different condition 2 there. We'll hit at that a little bit more tomorrow. So finally, this problem, a new drug, results in lowering the heart rate by varying amounts. In a 50-person sample, the average drop in heart rate is 5.32 beats per minute with a standard deviation of 2.49. Create a 95% confidence interval. Okay, so really we should, talk about the fact that we didn't really talk about a simple random sample in this. So you've got to question that a little bit. 50 is less than or equal to 1/10 of all people that, could possibly take the drug, so that's okay. And then it is 50, which is greater than or equal to 30, so we can use the normal curve. Okay. Again, we'll maybe be a little bit more explicit with this in the coming days. So our point estimate was 5.32. So 5.32 plus or minus. Since it's still 95%, we do 2, and then 2.49 over the square root of 50. Okay. So this ends up as 5.32 plus or minus 0.70. Okay, so our margin of error in this case is 0.70. So we've got 4.52 to 6.02. So again, we could go back and interpret that. We could say, well, we're 95% confident that the interval from 4.52 to 6.02 captures the true average drop in heart rate. Okay. Now, if we wanted to have the margin of error be smaller, okay, so right now it's 0.7. If we wanted to have it be 0.5, how many would we include in our sample? Well, so this really comes down to just saying, okay, well, this is the margin of error. How can we make that equal to 0.5? So 2 times 2.49 over the square root of n. And this has got to be less than or equal to 0.5. So if we divide both sides by 2, we've got that. I'm going to work over here. My work will get a little jumbled. I apologize. Square root of n is less than or equal to 0.25. So you can multiply both sides by the square root of n, then divide both sides by 0.25. So this yields, when you divide 2.49 by 0.25, it yields 9.96 is less than or equal to the square root of n. So you square both sides, of course, and we get 99.2 is less than or equal to n, which is always nice here because you have the nice little things, because we obviously can't round in terms of people. N has to be greater than or equal to 99.2, so n has to be 100. So here's what it kind of goes back to what we said, or I said on the previous slide, about why we sometimes don't care about larger sample sizes and what they do for margin of error. Is we had to double our sample size here from 50 to 100 in order to lose 2/10 on our margin of error. And a lot of times companies and pollsters just don't care. That's just not worth it. Doubling the sample size for that little bit of accuracy is not worth it. Okay, so the big thing out of this video is, well, making confidence intervals, interpreting the interval and level. The sooner you memorize those phrases, the better off you'll be. Don't forget to check your conditions. Every single time. It just should be an automatic thing.